So if you've taken linear algebra before, or if you have some idea of linear algebra, let's just get into the meat of the matter. And the meat of the matter is the first thing, or the main thing that we're interested in, is solving in linear algebra. The main problem is solving a system of linear equations, right? And you have all at some point solved a system of linear equations in high school, at IBA perhaps, and perhaps the simplest example of a linear equation is just simply, let's say, 2x minus y equals 0, x plus 2y equals 4, right? And that's a simple example of a linear system, right? A linear system of equation. And it's linear because both of these terms have degree 1. It's linear also because if you plot them on a two-dimensional plane, you will get a line. And so immediately the idea is, in this equation you have two unknowns, so two unknowns and two equations, right? And so you can see that there are two equations if you look at these line by line, and you can know that there are two unknowns if you go at it column by column, right? So you look at this first column, and the reason you can do that is that I've aligned the x's and the y's and the coefficients on the right hand side. So the idea is you keep the variables on the left hand side and you keep the constants on the right hand side, right? So this is a constant, right? And you must have seen a picture of this. I'm not sure if all of you are familiar with it, but a simple way to view this problem is to write it in matrix form, right? And so the matrix form is quite easy to see in that if you try to solve the system of equations, what really matters are these coefficients, right? And so you make a matrix of coefficients out of this left hand side. So that matrix of coefficient is 2 for x, minus 1, 1, and then 2. So that's my coefficient matrix. And then you have a vector which tells you what are the unknowns, so x, y. And then you have a right hand side equals to 0, 4. So this is the matrix form of your system of equations. And the way we write this is we say ax is equals to b, right? So where A is a matrix, x is written in bold and b is written in bold to denote that these are vectors, or perhaps instead of making this, we can just write them. We can say that this is a vector and this is a vector, right? And so what I'm calling a vector is basically a one-dimensional matrix which has one row and several columns, or one column and several rows, right? So this is something that I'm calling a vector, right? So x, y, so a column vector, this is technically x and b are column vectors. Okay, that's the first thing. So we're interested in really solving this system of equations, and this is a very simple system. This you can solve by elimination, by substitution. You know these methods and you can easily do that. What we're looking for is to find a method to solve this system that we can generalize to higher dimensions easily. So if now I move from 2 equations and 2 unknowns to 3 equations and 3 unknowns, so perhaps 2x plus y plus z is equals to 3, and then x plus y minus z is equals to 4, and x plus 2y plus 2z is equals to 5, right? And now you have 3 equations and 3 unknowns, and which you can again place in a matrix vector form, right? So you can just make the system by using the matrix of coefficient, turn it into a matrix equation by writing the coefficient matrix, which is 2, 1, 1, 1, 1, minus 1, 1, 2, 2. You have the unknowns in this vector, so this is x, y, z, and 3, 4, 5, right? And we're looking for, now the question, let's think about what do we want when we want to solve a system, right? When I say I want to solve the system, what does that really mean? So solving the system just means to find a particular value of x and to find an xy. So solving means find xy that satisfies all the equations, right? So I want an xy such that it satisfies this equation. So maybe you can immediately see that since the right hand side is 0, if you pick xy equals 0, 0, now that's some possibility of satisfying the first equation, because 2 times 0 is 0, minus 0 is equals to 0. So this satisfies the first equation, but if you plug it in, so it satisfies the first one, but if you plug it, excuse me, if you plug it in the second equation, so this is 0 plus 2 times 0, the left hand side becomes 0, the right hand side is 4, so it does not satisfy the second equation, and that's a problem. That's not a possible solution of this linear system because it doesn't satisfy both the equations, right? And similarly, the idea is, if I look at it in this 3 by 3 equation, and I'm calling it 3 by 3 because 3 equations, 3 unknowns, and if I want a solution to this system, I want a value of xyz that satisfies all the equations, right? Does that make sense? If you look at it from the point of view of this matrix vector equation, what I'm saying is I want, if I call this ax equals to b, that then I'm looking for an x that when multiplied by a gives b, right? So this is what's happening over here. This is a matrix times a column giving a column, right? And so if you're a little bit familiar with matrix vector multiplication, you know, so when can you multiply a matrix by another vector or another matrix? There are some rules, right? And the rules are as follows. So if you have ax equals to b, and A is, let's suppose, an n by n matrix, then x needs to have n rows, and in our case it has one column. And similarly b, so when you multiply this, I know that I can do this multiplication because the columns of A and the rows of x are same. So I can multiply these two together, and the result will be an n by 1 vector. And so the right hand side that I should have should also be n by 1, and in this case I do have an n by 1, where n in our case, so n is equals to 3 in our particular case. So we have 3 unknowns, 3 equations, and 3 unknowns, right? Any confusion so far? When we say n by n, we means n rows and n columns. So you look at rows times column. So n by n, 3 rows, this is the first n, and then columns, rows times columns. Okay, perfect. All right, so that's the first thing. So we're looking to solve this system. Now, immediately, I want to go ahead and think of this system in 2 different ways. I want to visualize this and something that Gilbert Strang calls the row picture. So let's look at the row picture of this system. And so the row picture of the system is basically saying that we look at the system of equations, and we look at the equations line by line, and we think of them, we visualize them in, so in our case this is a 2 by 2 system. Notice that I'm sticking for now with n by n systems. There are of course systems that might have more rows and less columns, so more equations, less unknowns, or less equations, more unknowns, but for now we're keeping the discussion to simple square systems, right? It's square because the matrix becomes n rows and n columns, so it's a square matrix, right? And so the first thing that I want to do is I want to visualize this in, I have a 2 by 2 system, so I'm going to visualize this in 2-dimensional space. So I have x on this axis and y on this axis, right? And so 2x minus y equals to 0 is, let's just try to find some points. This is of course going to be a line. If I plug in x equals to 0 here, I will get y equals 0, so this passes through the origin. If I put x equals to 1 here, so I can of course write this as 2x equals to y, and so x equals to 1 gives me y equals to 2, so 1 gives me 2. So the first thing that I have on my hands is a line. That's the visualization. That's the row picture of the first row, right? It gives me this line. Then if I try to do the same thing for the other equation, I get, okay, let's plug in x equals to 0 now. So I get 2y equals to 4, so y equals to 2. So this one starts off from y equals to 2. So this is over here. This is the starting point, and let's just use a different color so it's more clear. Okay, and so if I plug in x equals to 1 here, I get 2y equals to 3, and y becomes 3 upon 2, right? So y becomes 1.5, I believe. Okay, and so it becomes something like this at this point. It becomes, let me just check my calculation. So 2y equals to 4 minus 1 is 3, 2y equals to 3, y equals to 3 upon 2, right? So this is what I get. And if I make the line, of course, you can see that it's a linear equation. What I will get is a line. And so when I join these 2 points together, the reason I can join them with a line is because both of them are just equations of a line, right? They can be rewritten in the form y equals to, they can be rewritten in the form y equals mx plus c. They're both equations of a line, right? So m1 c1 or m2 c2, right? And so the row picture basically tells me that in 2 dimensions, when I plot them together, I get this picture. And notice that if I have a point that satisfies both these equations, then it's going to be on both of those lines, right? So it's going to be on this line and it's going to be on this line. And of course, in a visual picture, it's extremely easy to locate that point, right? It's this point right here, which is at the intersection of both of these lines, because I know that this point that I have here, it's not 1 exactly, it's between 0 and 1, because at 1 the value of the orange line was, so this was, at this point, this orange point was 1 comma 3 by 2, which is 1 comma 1.5, and this blue point is something like 1 comma 2, right? And at this point, you know, both of them are in the opposite direction, so it's going to be this point of intersection. I'm basically, when I want to solve this system, I'm looking for the coordinates of this point right here where they intersect. So basically, in 2D or in the row picture, it is the equation is in 2 dimensions, the solution is the point of intersection of lines, right? Okay, that's the row picture for a 2 by 2 system. Clear? The next thing that I want to look at is the column picture. So right, so the column picture, and I'm going to let's see if I can paste it here, right? Okay. Now the next thing that I want to do is write this equation, this system of equation, in a slightly different form, which is much more convenient to look at when we go to higher dimensions, because these lines turn into planes and then the planes turn into hyperplanes, and so in higher dimensions this column picture is much more useful, and even in algebra it's much more useful to look at this column picture. And so the way we'll turn this into the column picture is, let's go back to the matrix form of this system. Actually, let's take this form instead of taking the equations, and let's plug it here, right? Okay, so I have this matrix form, and now what I want to do is, notice that I can write, we can manipulate this system in this way. So you're aware of matrix vector multiplication, right? I can rewrite this system as if I multiply this matrix with this column, I'm sure you're aware that we do a row by column. So you take this row and you take the dot product. If you don't know what a dot product is, it's basically this time the first entry of this row times the first entry of this column, and the second entry of this row times the second entry of this column. And so this can be written as 2 times x minus y and 1 times x plus 2y, sorry, let's not write 2y, so 1 times x 2y. This is still a matrix and equals to 0, 4. Wait, sorry, what did I do? No, this should be a column. Oops. So it should be 2x minus y, and this should be x plus 2y, right? So this is a column. This is not a matrix. This has 2 rows, but it has just 1 column. The first entry is 2x minus y. So 2 rows. Let me remove this arrow. So it has 2 rows and 1 column. And let me remove this 2 from here because it looks like it's multiple. So 2 rows and 1 column. First entry is 2x minus y. Second entry is x plus 2y. Now you can of course ask, why did I, it's the same equation, right? You look at first entry is 2x minus y is 0, x plus 2y equals to 4. But now I'm going to do something different. I'm going to view them as a sum of column vectors. So now I'm going to rewrite this and I'm going to say, okay, you know what? I'm going to write this as, so x times the first column, which is 2 times 1, plus y times the second column, which is minus 1 times minus 1, 2, is equals to 0, 4. And so this is the column form, and in some it's also called a linear combination. This is a linear combination. So what you've done, I want you to understand and start using this term immediately. Get comfortable with this term. A linear combination is basically you take some vector, you multiply it with some number, you take another vector, you multiply it with some number, and then you add them together. So for example, a linear combination, so if I call this v1, v2, a linear combination of v1 and v2 is something like alpha times v1 plus alpha 2 times v2, right? So again, notice that this is a column vector, this is a column vector, and I'm multiplying them with scalars. So linear combination is basically scalar multiplication. What's a scalar multiplication? I'm just, this number that it's being multiplied with is the scalar multiplication, and then vector addition, right? So you do some scalar multiplication, and then do some vector addition. So what you will do is do vector addition. So if I want to go back from this to this form, I just have to multiply x with this column, y with this column, and then add the 2 columns together. So let's try to do that, right? Just so you get a sense of that I've not done anything illegal here. It's all mathematically valid. 2x, x plus minus y, 2y, and of course now if you add these vectors together, you get 2x minus y and x plus 2y. And you can add vectors if they're of the same dimension. So vector addition is only possible if vectors are in same dimension. I can't add, if this was a 3-row vector and this was a 2-row vector, I can't do that vector addition. But because this is coming from this system of equation, it's a consistent system, right? So so far I've just told you that I'm interested in this particular form. So this is the important bit. Let's write this bit down, and I really want you to, oops, did not copy perfectly. Let's get these braces down. Okay, and so I want you to immediately get familiar with this and get comfortable with this, that whenever you see a system of equation, you can see it as a linear combination of the left hand side. So this system, let's copy this, and now I don't have to do much work. I know if I want to write this, I can just follow the logic. So notice what happened here. X times the first column, x times first column, and oops, there should be a y here, and y times the second column is equals to the right hand side. So if I want to do that in a 3x3 system, it's just, I can now write x times the first column. So this is in linear combination form, x times 2, 1, 1 plus y times 1, 1, 2 plus z times 1 minus 1, 2. So this is essentially, I have given you another way of doing matrix vector multiplication, that you do these linear combination and add them together. You will get the same result that you get when you do simple row by column and row by column. So if you're frustrated by this method, if you don't like it for some reason, then you can just simply look at it in the form of a linear combination. So x times first column, y times second column, z times third column, right? And this is the left hand side equals to the right hand side, which is 3, 4, 5. All right. So this is to see the system as a linear combination of vectors. Does this make sense? So let's look at now I still haven't shown you the column picture. So let's take this system, and now let's try to build the column picture. So this was an example of 3 by 3. This was a 3 by 3 system. And now let's look at the column picture. What does the column picture look like? Okay, so here's the column. Now, if you've taken calculus 2, then you know what vectors are, right? So if you've not taken calculus 2 and or maybe you're not very comfortable with vectors, then you can think of vectors as arrows which point in the direction of whose horizontal component is given by the first entry and the vertical component is given by the second entry. So if I want to draw this vector 2, 1 in this two-dimensional space, so let's say this is y and this is x, this is my 2D space, and let's not call it xy, let's call it the first dimension and the second dimension. And if I want to write this as 2, 1, this vector looks like, let's start it from the origin, 2 times in the horizontal direction and 1 times in the vertical direction. And so this is my first vector, right? It starts from the origin and points in the direction of the horizontal 2 and vertical 1 direction, right? So this is 2, this is 1. That's the first vector I have. Okay, let's think about what happens when I multiply 2, 1 by, let's suppose, 3 times 2, 1. What happens? 3 times 2, 1 means the vector becomes 3 times 2, which is 6, and 3 times 1, which is 3. So if I draw this vector, and so notice that the first vector was 2 times 1, and if I draw 6 times 3, 1, 2, 3, 4, 5, 6, 6, and then 3, it will be somewhere over here. So this blue vector will be again in the same direction but longer, right? So multiplying, scalar multiplication. So at this point we know that scalar multiplication changes, or rather scales, right? Scale means to change the length, scales the vector. Now, of course, if I multiplied by -3, it would have become -6 and -3, which means it would have pointed in the negative direction. So it would have been something like this. So if you take all the scalar multiples of a vector, what you will do, so if I take all scalar multiples give you a line, So I can get any vector on this line if I just keep scaling this 2, 1 vector, right? So essentially we say that a vector spans basically a line, that you can get any vector along this direction. All you need to do is multiply this vector by some number, right? So that's scalar multiplication. That's the first thing. Okay, now let's draw this other vector that we have, and let's give it so -1, 2. So -1, 2 will be in this direction, and so I can write it like this. Let me just draw a line, and so I have this neat little line going here, and so this is my other vector, right? So this is 2 times 1 minus 1 times 2. Now, the second thing that you need to understand is how to do vector addition, right? So let's say I take these vectors, 2 times 1, so let's check what vector addition does. Vector addition is basically if I take 2, 1 and minus 1, 2, so 2, 1 plus minus 1, 2, if I add these two vectors together, on the first entry I get 1, on the second entry I get 3. So 1 by 3. Vector addition gives me another vector, a third vector, right? So, and if you want to visualize this, then what happens is basically the way we visualize vector addition is to draw, let's say this is the first vector, this was somewhat the first vector, this was the second vector, right? And the way we add vectors together is we take the second vector and basically shift it, make a copy of this. Let's hope it lets me make a copy of this. Okay, you take a copy of this and put it on the end of the first vector, right? And now we can join this together, and if you check what happened here, so 2 plus minus 1, if you notice that if I start from the origin and go to the end of the second vector, notice, oops, okay, I should just take the really bad at drawing lines, so so this vector that I've gotten, notice that its horizontal component is 1 and vertical component is 3. Notice this. Okay, so I have, let's just shift to the, yeah. Okay, so this was 1, 2, this was 1 and this was 2, and notice that I was 2 times in the horizontal direction, subtracted 1, so I was once in the horizontal direction, so this vector that I have has 1 in the horizontal direction, and I was 1 in the vertical direction with this vector, and I added 3 more, so I got 2 more, and I got 3 in the vertical direction. So this vector gives me this is the vector addition, right? So putting it on the tail of putting the second vector on the tail of the first one. So, and if you can also, by the way, complete this picture. There was no need for me to start from the copy of this and copy of this vector and bring it here. I could have taken the other route as well. I could have just taken this vector over here. Let's see if it lets me do that, or maybe, you know what, I can simply draw this. So if I take this same vector and do something like start from here and draw it here, notice that I still get the same point. So this vector doesn't matter which direction you take it in. If you take the first vector and then go to the second vector, or you take the second vector and then go to the first vector, the resultant vector addition is the same. And this is basically saying that if I had done something like maybe if I had did it in the other direction, I would, if I had said minus 1, 2 plus 2, 1, then I still get the same thing, right? Minus 1, 2 is 1, 2 plus 1 is 3. This is vector addition, doesn't matter in which order you do it, it's still going to be exactly the same, right? And so this gives me the picture of what happens when you do vector addition, and this tells me what happens when you do scalar multiplication. And now the big question of how does this relate to this picture here? So now this is telling me, now let's read this equation in terms of scalar multiplication and vector addition. So what's happening is this vector is being scaled by x. This vector is being scaled by y. So scaled by y. And then we're adding them together, right? And so some length of, we change this vector a bit and we change this vector a bit, and the result that we want, the vector that we get by after we add those changed vectors, is I want that vector to be 0, 4, right? So I want this to be equals to 0, 4. I want to get this vector by multiplying something with this, changing this scale of this, and then, so maybe, you know, if I start off and if I take this vector, let's say I take this vector, and if I just put it over here maybe and start scaling it, and try to see if I reach the end of the original vector, you notice that if I put it exactly, I know I have not drawn this to scale, so I must be getting some error. Notice that I can almost get in the same direction, but I have overshot it a bit, which means maybe I should reduce the length of the first vector, right? So the idea is adjusting this x and adjusting this y, so that once you add them together, the result that you get is the same as this vector, right? So I'm going to reverse that process now, and we're going to try to find the solution. So let's just try to find the solution of the system. So 2x minus y. So let's do this. So 2x minus y is equals to 0. That was the first system. And x plus 2y equals 4. X plus 2y equals 4. And I'm going to, let's suppose, use the elimination method. So what I'm going to do is multiply this equation by minus 2. So multiply by minus 2. What do I get if I multiply this equation by minus 2? I get minus 2x minus 4y is equals to 4. So this was my first equation. This was my second equation. Let's call this equation 2 star because I've gotten it from 2. So I just took this equation and multiplied it by minus 2. I'm just trying to solve the system of equation. There's nothing new. I'm sure you must have done it 1,000 times. So now I add 1 and 2 star together. I get 2x minus 2x, I get 0. Minus y minus 4y, I get minus 5y equals 4. And then y is equals to minus 4 upon 5, right? Okay, that's the first solution that I'm getting. So minus, is that correct? Minus 2x. Let me know if I'm making any errors. Minus, oh, what, sorry. Oh, yeah, you're absolutely right. This was supposed to be 8, minus 8. Did I make any other mistake? So this was minus 8, and now this should be 8 upon 5. Is this correct now? Seems to be. So yeah, seems to be the right one. Okay, let me know if you find any mistake in this, but let's move on. So now the other thing that we can do immediately is, now that I have one of these values, let's just go and plug it into the first equation. So 2x minus y is equals to 4, 2x minus 8 upon 5 is equals to 0, and x is equals to 8 upon 5. So I get x is equals to 4 upon 5, right? So the solution that I'm getting is 4 upon 5, 8 upon 5. And now let's go to the column picture and see what this means. So what the column picture is telling me, that scale this vector by 4 upon 5 and scale this vector by 8 upon 5, right? So x is 4 upon 5, so x is 4 upon 5, and y is 8 upon 5. Now 4 upon 5 is something like 0.8, and 8 upon 5 is 1.6, I believe, right? And so it's telling me that I need to decrease, because it's less than 1, it's going to decrease the size of the first vector and increase the size of by about 60% and decrease the size of the first vector by 20%, and I should get that vector. And sure enough, it seems that if I take something like this, if I stop this vector at 80% of its value, right, something like this. Let's just use the line tool because I don't think I'm great at this. So let's just, okay, this is what I get if I stop at about 20% of the first vector. So scale it down and scale up the other vector, right? So I want to increase the size of this vector by about 60%. I scale it up. So let me just do it over here. I think this should be about enough in the same direction. And what I should get if I add them together, so to add them I need to pick it up and put it at the end, and so sure enough it seems that I will reach about the same point, right? Of course I've not drawn this accurately, but the idea is that if you decrease the size of the first vector and increase the size of the second vector, your result is the new vector 0, 4, right? And that's the column picture. So this is the column picture, right? So column picture. That what I want is I want to take, in other words, I want a linear combination, the linear combination of vectors to give me the right hand side vector. Does that make sense? So all I'm looking for is some linear combination, scale this vector, add them together and reach the second vector. So in other words, you can think of it as joining them in some way, you know, increasing the length, decreasing the length in such a way that they reach this point. And of course, now that we found the solution to this system, we can go back and say in the row picture, the solution that we were looking for, this solution, since we have a solution, this intersection point is 4 upon 5 and 8 upon 5, right? So the coordinates of this point in the row picture are 4 upon 5 and 8 upon 5. And in the column picture, these 4 upon 5 and 8 upon 5 indicate how much I need to scale these vectors before adding them to reach this other vector, right? Okay, so now by the way, this picture that we've just seen is not a new picture. This is a picture that you've already seen made of some other vectors that you start off with plotting, right? So for example, let's look at the column picture of the easiest possible system of equations. And what is this easiest possible system? Let's suppose I write a system of equation x plus 0y is equals to 5, and I write another system 0x, let's erase this, 0x plus y is equals to 4, right? What's the solution of the system? What's the values of x and what are the values of y that can satisfy both of these equations? It's a very easy system to solve. X is equals to 5 and y is equals to 4. It's not even a system of equations, it's just saying the value of x is 5 and the value of y is 4. But I have disguised it by making it into a system of equations, right? So x is 5, y is 4, that's the system. But I've written it in such a way so that we can visualize the column picture. And now let's turn it into the column picture, and we turn it by saying x times the first column is 1, 0, plus y times the second column, which is 0, 1, is equals to 5, 4, right? And now what I'm doing is, it's an extremely simple picture to make, and you've made this picture many times before, which is 1 times 0, x times 1 times 0 is basically you're saying I'm going to take, and you've already found the solution, which is 5. So my standard vectors, these are called, by the way, this 1, 0 and 0, 1 are called the standard basis vectors. These are terminologies that I have not explained in detail, I'm just introducing them, but you can get some sense of why we call them the standard basis vectors, right? Because this is just 1 in the 0, 1, 0 is just a vector of unit or vector of length 1 in the horizontal direction, and 0, 1 is a vector of unit length 1 in the vertical direction. And the idea is now, how can I combine these together to reach vector 4, 5, 5, 4, is I want something like 2, 3, 4, 5, and 1, 2, 3, 4, and I want to reach this vector. So let's draw that vector from this point to this point, and it's extremely easy to take a linear combination of these two vectors, right? I know that if I want to reach this point, because this standard basis vector only goes in the horizontal direction, I can just scale it to the length of the horizontal direction of the resultant vector. So I know I can take it as far as this, and the other vector won't mess with this because it's in the vertical direction. And now I scale this other vector in the vertical direction, and there you go. This is 5 times the first vector, 4 times the second vector, and it's the easiest system in the world to solve, because it's really not a system, it's just a solution given in a very disguised way. So what I'm trying to say is that this column picture is not new. The only difference is that instead of the standard basis vectors, you have some vectors that are not just in the horizontal direction, not just in the vertical direction, but you have vectors going in some other tilted direction, and now you want to see how can you combine these to get to the resultant vector that we want. Because if I had wanted, let's suppose, to get to this solution by just the standard basis vectors, I don't need to do anything. I can ignore the horizontal direction, just go in the vertical direction. But that's not what we want. We want to find a way of combining these two vectors to get this vector, right? And that's essentially changing the view of, okay, I want to find a set of values to solve my system of equations. You can just view it as combining these vectors to get to this vector. And I'll discuss this column picture in a bit more detail later on, right? Now that's the first thing that I want you to know. Okay, is that clear so far? So the row picture, column picture is clear. Okay. Now let's step back from solving system of equations, and just discussing the idea of linear. Oops, let's change that. Let's discuss the idea of linear combinations, right? So I take the same vectors that I already had, let's say 2 times 1 and minus 1 times 2, and I'm not trying to solve a system now, I'm just trying to look at what possible linear combinations I can take. 2 times 1 and minus 1, 2, and this is, and now I'm thinking of, let's take some possible linear combination. So maybe I can multiply this with 1 and this with 1, and I get, what do I get? 2 minus 1, 1, 1 plus 2, 3. So that's one possible linear combination. Another combination can be I multiply this by 2, 2 times 1 plus 1 times this minus 1 times 2. So I get 4 minus 1 is 3, and 2 plus 2 is 4. So that's another vector that we can get. So I can get this vector. If I take 2 of this vector, 1 of this vector, I can get this. If I take 1, let's say 3 of this vector, 2 times 1, and none of this vector, 0 times this vector minus 1 times 2, then it's just, this vector is ignored, it's just a scaling of this vector, right? So this is 6 times 6, 3, this is the vector. And so what I'm basically trying to do is I'm trying to find out what vectors I can reach, right? So what possible vectors can I reach if I take different combinations of these vectors, right? So let's say, let's take one more, let's take minus 1 times this, and which is 2, 1, and plus 2 times this, which is minus 1, 2. So at this point I get minus 2, which is, okay, let's make this interesting. Let's take plus minus 2 of this. So, or let's just ignore minus here and let's just put a plus here, right? Okay, so 2 minus 2, it gives me 0, and 1 plus 4 gives me 5, right? Okay, and so these are the possible vectors. I've just taken a few combinations. There's of course lots and lots of numbers that you can take. You can take half times this and 5 times this, or 6 times this and 3 times this. There's infinitely many possibilities, and what I'm interested in seeing is what I'm calling is, let's say 2 times 1. So I got the vector 1, 3. So let's just try to draw these vectors. So the first vector is going to be something like, so the first vector is going to be something like 1, 3. Let me just put some tick marks here so that it's somewhat roughly to scale. 1, 2, 3, 4, 5, 6, minus 1, minus 2, minus 3. 1, 2, 3, 4, 5, 6, minus 1 plus 2. Okay, and so let's try to draw all these vectors, right? So I can reach vector 1 times 1, 3. That's the vector I can reach. I can reach vector 3, 4, which is 3 in this direction and then 4 in that direction. Oops, let's write that. So 3 in this direction and 4 in this. Don't? No? What? Okay, I'm just going to leave it here. Think of it that I've made it to scale. It's just, let's see. Don't. Okay, I think this is good enough. It's not really, it's fine. Okay, 6 times 3, so sorry, I keep saying 6 times 3, that's, I'm being very imprecise here, it's vector 6, 3. So that's the vector 6, 3, and I can also reach vector 0, 5, so I can reach vector 0, 5. So it seems like I can sort of go in any direction that I want with these two vectors, right? I can go in this horizontal direction, I can go in this direction, this direction. We also saw that we can combine them to get the vector 0, 4. I can even go in this vertical direction. And if I want to go in the other direction, it seems like maybe I can find it in this direction. And there's nothing really stopping me from taking some linear combination of them and going in any direction that I want. And so I want to give this a special name, and this name that we give it in mathematics is that we're basically looking at the column space. Column space. So this term space will make it more precise later when we talk about vector spaces, but there's really nothing really stopping us from looking at how we can combine two vectors together and get all the possible vectors. So column space is basically all possible vectors given by the linear combination. So let's call this vector v1 and v2. So the column space of v1 and v2 is all possible vectors given by the linear combinations of v1 and v2, right? So we're basically trying to see, okay, which vectors that I can get, and it seems like all of these vectors are in the column space, and I'm going to make a bold assertion here, is that it seems like the column space is just going to be this entire three-dimensional space, right? There's nothing really stopping me from, two-dimensional space, there's nothing stopping me from reaching this entire space. So it seems like the column space will be this entire space. I can get to any vector in this 2D space. So I'm going to say that the column space in this case is, so the column space of v1 and v2 is the whole two-dimensional space, because I can get any direction that I want, right? Okay, that's the column picture. And so I've talked in detail about the two-dimensional picture, and so let's just end this lecture by discussing for a moment the row picture and the column picture for the three-dimensional space, because at that point, after that, we can't really discuss the row picture and column picture anymore, but because our visualization ends at 3 dimension, we don't really have a good way to visualize 4 dimensions, but let's talk about the 3 dimensions while we can, right? So this is the 3-dimension picture, and let's just discuss what the row space and the column space looks like this. So row picture and the column picture looks like in this. So now I have a linear equation in 3 dimensions. Can I get an answer to what will it look like if I plot this separately? Not talking about the row, I'm just talking about the row picture right now. So I want to plot this 2x plus y plus z equals to 3. What does it look like in a 3-dimensional setting? What does a linear equation make in 3 dimensions? Has anyone taken Cal 2 here so far, or has anyone seen what we get when we take possible combinations of x, y, and z, linear combinations of x, y, and z? Anyone with some Cal 2 background? Okay, let's just make that picture. So the answer is for this that in 3 dimensions, if I have a linear equation, the result is a plane, right? So you get 3 different 2-dimensional planes. It doesn't make a line, Danya, it makes a plane, it makes a 2D plane, and let me just draw that plane. So let's see if I can find a point that it passes through. So 0, 0, z is equal to 3. So it looks something like this, right? It's a 2-dimensional plane. Let's see if I can draw this nicely. It's something like this tilted, imagine a piece of paper tilted in 3 dimensions, right? So you get essentially a page in 3 dimensions when you try to visualize what you get from a linear equation in 3 dimensions. And so this is one equation. The other, of course, now what about the other possible plane? So this is another plane that we get. So this is as equals to 4. So maybe this plane, this other plane looks like this. So I have, if I combine this plane and this plane, sorry about how ugly this is, and I have another plane, a third plane, right? So maybe something like this. So I have 3 pages basically tilted in different directions, and what I'm looking for is that point. So let's visualize what happens when, if I take one page and put, let's say, another page like this, and so notice that they will intersect on a line. So these two are going to intersect on a line, and if I put in another one there, then it's possible, exactly, combination of many lines that make a plane. So now I want to know that at what point, so it seems to me that these might intersect at this point, at this line, these might intersect, and I'm looking for some common point. So maybe something like this, it extends in the horizontal direction and the vertical, all of these possible directions. And what I'm looking for is that one point that is common to, sorry about that, that is common to all of these planes, right? So these planes are going to intersect, 3 possible planes can intersect at one point, and I want the coordinates of that point, right? So I'm looking for the coordinate, and now you can see already this picture is a bit messy. I don't really want to deal with these planes, and if I go into 4 dimension, I have no chance of visualizing this. But the column picture, if I look at the column picture, it's still, I need to just let this go and put this here. Okay, now the column picture is still as neat and tidy as it is in the 2 dimensions, right? So if I look at the column picture now, it's telling me, okay, the column picture, let's take this and let's take this. This is my x, y, and z direction, right? And so the column picture, let's draw it, let's write down the equations. X2, 1, 1 plus y, 1, 1, 2 plus z, 1 minus 1, 2 is equals to 3, 4, 5. So again, I'm asking, how will I take a linear combination of x, y, z and get this right hand side? So let's draw these 2, 1, 1, maybe looks like something like this. So let me erase this vector. Imagine that we're talking about a 3-dimensional plane, so I can go in horizontal direction, vertical direction, and inside and outside the page. And so the vector 2, 1, 1 will look like 2, and let's say 2 in this direction, and then 1 in that other direction, something like this maybe, and then 1 in that direction. So this looks like maybe something like this. So 2, 1, and then 1. So this was my y-axis and this was my z-axis, right? So this the first picture. 1, 1, 2 looks like 1, 1 in this direction, and then 2 in this direction. So this is going sort of inside the page. And then again 1, minus 1, 2. So 1, then minus 1, and then 2. So again, I have 3 different vectors, and now I want to combine them together in such a way, scale this a bit, scale this a bit, scale this a bit, and add them together to get the vector 3, 4, 5. So vector 3, 4, 5, so the right hand side that I want is 3, in this direction, and 4 in this direction, and 5 in this direction. So I'm looking for some combination of these 3 vectors. When I add them together, scale them a bit, add them together to get somehow, let's say, to this vector, right? Maybe it looks like something like, I don't know, this, and then this, and then, oops, then something like in this direction and something like in this direction. So I'm looking for getting these 3 vectors combined in a way such that I can reach this other vector, right? So that's the column picture that I want. Okay, I'm going to stop at this point because I believe that's enough for today. That's a good start, right? I just want to leave you with a few questions. The questions are as follows. These are the central problems of linear algebra, which is, does every linear system have a solution, right? Think of it in another way. The same question can be written as, can we solve ax equals to b for any vector b, right? And if you think about it in another way, so this is in the matrix form, this is the same question written in matrix form, this is the question asked about linear equations, so this is in the form of equations, this is in the form of matrices, and now I can again ask the same question in a different way, which is that do the linear combinations of vectors of the columns, right? So what I'm doing is I'm taking a linear combination of the columns, and so if I'm asking, can I reach every possible b, then I'm basically asking, can I take some linear combination to fill the entire space? Because unless and until I can fill the entire space, I won't be able to solve it for every possible b. If I get it for every possible b, that means that I can fill the whole space. So then the question becomes, do the linear combinations of the columns fill the whole space, right? And this whole space can be R2 or R3, 2 dimensions, 3 dimensions. For now, let's keep it to 2 and 3 dimensions, and let's move to higher dimensions once we are comfortable with matrices and elimination and so on, right? So this is the basic idea of linear algebra. These are the basic setup. I want you to get comfortable with these terms: linear combination, column picture, row picture, column space, linear combination, vector addition, scalar multiplication. These are all terms that we will need once we start solving these equations, right? So that's the basic idea. Okay, right, so the logistics. Okay, any questions, any confusions, let me know. I'll stick around for a few minutes. If there are no questions, we can just end this live feed, and we'll start on Wednesday, same time. I won't be doing a session on Google Meet. We'll just jump right into the YouTube video and discuss the second lecture. Okay, so this lecture is sort of a introductory lecture, which is not from, I don't think the first chapter of the book discusses this. I think you will find this in 1.1. Some of this material should be in chapter 1 of Gilbert Strang's book. That's the one that I'm using. So look that up. I'll send you the book when I get once the class ends, I'll send you the book. Okay. But this is all introductory material. You may not find it in the same way as I have stated it. There are some terms that I've introduced immediately, which I think is important. But from the next class, we'll be following more or less strictly the book, the chapters in the book. So the sequence of the book will be more or less strictly followed. Okay. Any other questions? feel free to send me any feedback that you have for these lectures. If you think there's any way we can make them better, let me know, send me an email. Otherwise, I'll just stick to the way that I'm dealing with things. So I'm gonna fade to black here. And have a good day.